Okay, this video will be your review for our intro to vectors and vector applications. For the first couple of problems, we are just going to go through some of our basic stuff. Notice that we need to give our component form, magnitude, and direction angle for each one of these. So for the first one, we need to really first go to that component form because that's going to make things a little bit easier for us. So our component form for this vector AB is going to be equal to, and remember that's the difference of your x's, so -1 minus a -7, so that's going to give you 6. And then -4 minus a 4, that's going to give me -8. Now for part B, they want us to give the magnitude. Well, if we have our component form, then the magnitude of vector AB is a little bit easier to find. It's just going to be the square root of 6 squared plus -8 all squared. And so that's going to give me the square root of 148, and you're welcome to leave it just like that. And then we need to finally find our direction angle, and this is where we plotted to see where our vector would be. We're over 6 down 8, so we have 6 and -8. Our angle that we find is sitting inside the triangle, and so we're going to say tangent of theta equals -8/6. And then to find that actual angle, we need to do the inverse tangent of -8/6. And that's going to give us -53.13. And again, that's going to be the angle inside the triangle, but our direction angle will be the angle formed between this initial side and that terminal side. So we're going to have to take 360 degrees, and we're going to subtract out our 53.13, and that's going to give us 306.87 degrees. All right, number 2, working the same way, we will first need to find the component form just simply because it makes things a little bit easier for us. And so the component form for vector RS is going to be 2 minus 4, and then 9 minus a -3. And then our B part, to find our magnitude. So the magnitude of vector RS, that's going to be the square root of 4 plus 144. So that's going to give us the square root of 148. And then we're going to find our direction angle. And again, I would use our component form to plot this. We're going to go back to and up 12. So we have our triangle, and inside there's our theta. And here's our side lengths, and so we're going to say tangent of theta equals 12/2, and so our theta is going to be inverse tangent of 6 if you want to go ahead and reduce that. And so let's see what that's going to give us. We get 80.54. And again, that's this angle inside here. However, the direction angle is going to start here at our initial point in standard form at the origin and go around to there. So we know the complete revolution all the way over to here is 180. So if we take our 180 and we're going to subtract our 80.54, that inside angle, that's going to give us the outside angle, which is our direction angle. And that's going to be 99.46 degrees. Now looking at our other example, for this one you have to be careful picking your initial and terminal points. Your initial point is up here, and that initial point should be 5,2. And our terminal point down here should be 2, -4. And so now for our vector form or component form of vector LM is going to be -3, 2 minus 5, and -4 minus 2. So that's going to give us -6. And then if we need our magnitude, which is again the length of that vector, the magnitude of this would be the square root of 9 plus 36. And that's going to give us the square root of 45. And then finally our direction angle. It looks like we're going to be in the third quadrant. We're going to be down here. And we have -3, -6, and theta sitting inside there. So tangent of theta is going to give us opposite over adjacent. And so we're going to find our angle inside there to be, it's going to be 63.43 degrees. And again, that's your inside angle, but if we go look at our direction angle, we would have to have started here, initial point there at the origin, and it's going to go all the way around. So I need to come back and add 180 to that, and so that's going to leave us with a direction angle of 243.43 degrees. Okay, for the next set, we are doing our vector operations. And so for our first set here, we really can think of this as the distributive property. So we have 3t minus r. So what we're going to do is substitute in place of t that vector, and it's in component form. And that vector is 5, -1. And then I'm going to subtract vector r, which is -6, -4. And so if you want to go step by step, you can go ahead and show this product of the scalar and the vector to be 15, -3. And then I'm subtracting from that -6, -4. And so really that's going to end up giving us 15 minus a -6, so 21, and -3 minus a -4 is going to give us a +1. So we're going to get 21, 1. Now for number 5, again, very similar, same idea here. So I'm going to take my 5/2, and I'm going to multiply that to -6, -4. And then add to that 4 times vector s, which is -2, 7. And so if we want to go ahead and distribute here, we're certainly welcome to. And if we do that, then we're going to end up here. Let's see, 2 cancels into 6, leaving 3, so -15. And then 5/2 times -4, that's going to give me -10. And then I'm adding to that -8 and 28. And so finally we're going to have -15 minus 8, so I'm going to get -23, and -10 plus 28, so I'm going to get 18. All right, so now for our next problem, we need to find the unit vector in the same direction as vector v. So the first thing we need to do when we're finding the unit vector is we need the magnitude of vector v. And since we're in component form, that's just going to be 8 squared. So that's going to be 64 plus -4 squared. And so that's going to give us the square root of 80. And now for this one, we do need to reduce that. That's 16 times 5, so that's going to give us 4√5. And we're doing that so we can reduce down our unit vector. And so our second step is going to be our unit vector. Is going to be equal to 1 over the magnitude times the component form 8, -4. And when we're multiplying that through, we do have 8 over 4√5, so that's going to be 2 over √5. And then we're going to get -1 over √5. And most of these you will see rationalized. So we're going to multiply top and bottom by √5 over √5 to get that rationalized. So that's going to be 2√5 all over 5. And then same process here, I'm multiplying top and bottom by root 5. And so that's going to be negative root 5 over 5. All right, for these we need to change this into our linear combination. And do remember that this all came from our I value times 1, 0, and then plus our j value times 0, 1. And if we look at that broken apart, then that negative 1 is going to be times vector I plus negative 3 is going to be times vector j. So we have negative I minus 3 times j. All right, and then the same idea over here on number 8. However, we do need to get this vector in component form first. So when we rewrite that, we're going to have negative 2 minus a negative 6, negative 8 minus 1. And now we're ready for our linear combination, which would just be 4 times I minus 9 times j. Okay, for this next set, we have a vector that we need to write in component form, and we're given the direction, angle, and we're given the magnitude. Now remember, the formula for that is going to be the magnitude of vector v times cosine of our direction angle, comma, magnitude of vector v times sine of our direction angle. So now while we're plugging in for this one, we're going to have 14 times cosine of 135 degrees. And then we're going to have 14 times sine of 135 degrees. And if we continue here, then that's going to be 14 times root 2 over 2. And it's going to be negative because of the quadrant. And then 14 times, again, that's going to be positive root 2 over 2 because of the quadrant. And so our final answer here would be negative 7 root 2 and positive 7 root 2. Now you are welcome to put this portion in your calculator if you want to and give the decimal form of that. All right, number 10, same process again. So for this one, we're going to have 3.5 times cosine of 210 degrees, and then 3.5 times sine of 210 degrees. All right, and so here again, going through that process, and you can do the exact form or the decimal version of this. The exact form of cosine of 210 is negative root 3 over 2. So we have 3.5 times, and then we have negative root 3 over 2. Oop, we need a comma there. And then 3.5 times, and then sine, the exact form of sine of 210 is going to be negative 1/2. And so working all of that out, and by all means use your calculators if you want to, you're going to end up with negative 7 root 3 if you go through the long process over 4. And then over here you're going to get negative 7 over 4. And to do that by hand, of course, you would change 3 1/2. Remember, that is the same thing as 7/2. So multiplying, that's where the 7 comes from, and where the 2 multiplies to give you the 4. Okay, now for these, we're going the other direction. So we're given our component form, and we need to go through and find the trig form. And the trig form was what we were just doing with the previous problems, number 9 and 10, the formula that we were using there. So working this one through, the first thing we would need would be the magnitude of vector p. And so that's going to be the square root of 2 root 6 all squared. So that's going to be 4 times 6. So that's going to give us 24. Plus, and then here square this one, that's going to be 4 times 2, which is 8. So the magnitude here is going to be the square root of 32. And again, you can leave it like that if you want. Now we need to do our direction angle. So tangent of theta Remember, it's going to be opposite over adjacent, so that's negative 2 root 2 over 2 root 6. And so when you find that angle, keep in mind that you're going to be in the fourth quadrant. So you're down here, and I know that from these values here, positive x and negative y. And so inside here, that angle that you find, which is probably 30, it's going to be 30 degrees, or in your calculator, you should get negative 30. But keep in mind your direction angle, again, your initial point there at the origin, it's going to swing all the way around this direction. So my actual theta that I need is going to be 330 degrees. And that's just like the previous problems. So now we're ready to go ahead and write our trig form. Our magnitude was the square root of 32 times, and then I'm going to have cosine of 330 degrees, and then sine of 330 degrees. And you're welcome to leave it just like that if you want. Now, number 12, we need to note that if we're looking at 5i plus 12j, that's really in our component form 5, 12. That's all that linear combination is telling us. So the magnitude of vector v is going to be the square root of 25 plus 144. And so that's going to give me the square root of 169, which is 13. And so now we need our direction angle. So again, we would say tangent of theta, and you can plot this if you want to. You're in the first quadrant. It's going to be opposite over adjacent. And so we're going to end up inverse tangent of 12 over 5. And that's going to give us 67.38 degrees. And that is going to be our direction angle because you're in the first quadrant. And so for that one, we're ready to go ahead and write our trig form. So we have our magnitude, which is 13, times, and then we're going to have cosine of 67.38 degrees, comma, sine of 67.38 degrees. All right, and so now we're going to number 13, and this one I would change it to component form before I do anything else, just because it's a little easier to work with. And so vector xy in component form is going to be negative 1 minus 1, so negative 2, negative 9 minus 5, so that's negative 14. And so now we're ready to look at the magnitude of vector xy. And that magnitude is going to be the square root of 4 plus, and 14 squared is going to be 196. So that's going to be the square root of 200. And then we're going to go through and find our theta. Let's see, we're going to say tangent of theta is going to be our opposite over adjacent, so that's negative 14 over negative 2. So that means theta is equal to, and if we do that, keep in mind you're in the third quadrant, so what you find, you're going to have to add to 82, and that should generate for us 261.87 degrees. So now we're ready to write our trig form of our vector. The magnitude here was going to be the square root of 200 times, and then we're going to have cosine of 261.87 degrees, and then sine of 261.87 degrees. All right, so number 14 is telling us that we have two construction workers lifting beams using ropes. Worker A pulls with a force of 500 newtons at an angle of 40 degrees with the positive x-axis. So if I sketch out, and so for 40 degrees, that's going to be our first. So that's about here maybe. So 40 degrees. And then let's see, worker 2 or worker B has an opposite side pulling with a force of 380 newtons at an angle of 115 degrees. So that's going to change here, 115. It's going to be back out here somewhere. So now that angle is going to be 115 degrees. And so with the positive x-axis, so we have that drawn. And so for A, we need to find the magnitude, and for B, the direction angle of the resultant force. So the resultant force will be these two vectors together. So let's go ahead and set it up. Okay, so for worker A, we're going to call that our vector A. So over here to the side, I'm going to set up vector A, and that's going to stand for worker A. Oop, I need to put that in red. Sorry, guys. All right, so worker A, he is pulling with a force of 500 newtons. So we're going to have 500 times cosine of 40 degrees. And then we're going to also have 500 times sine of 40 degrees. And so that's going to represent worker A. And then we need our second vector. That's going to be for worker B. And that vector, he was pulling at a force of 380. So we're going to have 380 times cosine of 115 degrees. And then 380 times sine of sine of 115 degrees. All right, so our resultant vector is going to be the sum of vector 1, vector 2. That's our resultant. So vector A plus vector B. And I would put all of this in our calculators for sure. So when we add these two similar components, the first components together, you should get 222.43. And then when you add our second parts together, you should end up with 665.79. And so there's your resultant vector for those two. And it wants the A part, the magnitude. So now that we have that in component form, we can talk about our magnitude. So the magnitude of vector A plus vector B, my goodness, is going to be equal to, and we're going to have the square root of 222.43 squared plus 665.79 squared. And so that magnitude there is going to be 701.96. So that's going to be our first O, and we need our units. What was our units? Newtons. Okay, now we need to go find our direction angle. And so very similar, we're going to use that component form. And so looking at our angle, we're going to have tangent of theta is going to be equal to, and we're going to do our opposite over adjacent. So that's going to be 665.79 over 222.43. And so solving for just theta is going to give us 71.526. And that's going to be our direction angle. And we know that simply because we stayed with that positive x-axis. For the last two problems on this problem set, we will be picking those up with our next setting. So for 15 and 16, those will not be on our test.